to be between 0 and 1. So just kind of to model all variables which have values in a finite interval, but usually kind of very often for variables which takes value in interval from 0 to 1. So it's something like a fraction of some quantity. So sometimes, for example, it's used to model probability kind of itself, so in Bayesian analysis. So this is a random variable x with beta distribution belongs to 0 and 1. So and it's called is a beta random variable with parameters alpha and beta, and these parameters should be greater than 0, also should be non-negative, so otherwise it's doesn't work. So it's beta distributed random variable, beta random variable if its density is so it's f of x, and it's equal to x to the power n. Well, kind of it's usually written alpha minus 1 and multiplied by 1 minus x beta minus 1. Right? So now so this is a positive quantity, but we also need to ensure that its integral is equal to 1, so we just divide by some constant which depends on alpha and beta. So, and we call it so beta of alpha and beta. Right? So kind of, and so of course kind of this thing b alpha and beta is just defined as an integral from 0 to 1 from this x alpha minus 1 and 1 minus x beta minus 1 dx. And well, this integral can be calculated for some, say, integer alpha and beta. And from this calculation, one can guess what's the formula for this constant. So it turns out that this is equal to gamma alpha divided by gamma beta. So gamma alpha plus beta. So it's not necessary to remember all this. It's just kind of, well, so this constant is something like something which can be calculated. So if alpha and beta are integers, then this is just some combination of factorials. Right? So some multiplication of factorials. So for example, so if you have a alpha is equal to 2 and beta is equal to, so if parameters are 2 and 2, right, in this case you will have a integral, right? So integral from x 1 minus x, right? So alpha minus 1 is 1, beta minus 1 is 1, so dx, and so kind of 0 to 1, and in order to calculate it, so it's clearly that we can calculate it, but it's also possible to use this formula, and in this case what you will get here is you'll get gamma of 2 divided by gamma of 4, right? So by this formula, just using this formula. And in this case, so kind of gamma of 2 is equal to 1 because it's 1 factorial. Gamma of 2 is equal to 1 factorial, so it's equal to 1 divided by, and gamma of 4 is 3 factorial. Right? So kind of, it's just kind of strange thing, but gamma of x, if x an integer, is equal to x minus 1 factorial. So it's equal to 1/6. Right? So in this case, the density is okay. So 1 divided by 1, 6. So it's 6x 1 minus x. So this is the density in this for this specific case, for this specific choice of the parameters. This is the density, and kind of it's if x belongs to the interval from 0 to 1 and 0 otherwise. 0 otherwise. And so this is an example of this random this distribution of this random variable. Now, another very special case. It's kind of another example. So this is example 2. So a special case when alpha is equal to 1 and beta is equal to 1. And in this case, if you look at on the formula, and you see that x to the power of 0 and 1 minus x to the power of 0. So it's just equal to 1, right? So x to the power of 0 is 1. 1 minus x to the power of 0 is also 1. So in this case, kind of it's a constant density. Right? So so in this case, the f of x is equal to 1, and we know kind of there shouldn't be any kind of additional constant. So integral from 1 over interval from 0 to 1, 0 otherwise. It is equal to 1. So kind of this shows that with one particular case, this particular case of a beta distributed random variable is a uniform distribution. So uniform distribution is a particular case of beta distribution. And so this is a kind of the role of a beta distribution is just a generalization of a uniform distribution. So if we model kind of a distribution random variable which takes finite values on a finite interval, we also want more flexibility with just having a uniform distribution. And this beta distribution provides some 2 additional parameters. So if kind of it's kind of if kind of this density can be plotted, and it kind of have a lot of different possibilities for the form of the density. So it can be so it can be flat like that, right? So this is a kind of alpha is equal to 1 and beta is equal to 1. Typically, it's kind of something like that. Right? So in this case, with alpha greater than 1 and beta greater than 1, but alpha and beta are equal to each other. Or it can be kind of if, say, if you have alpha greater than beta. So say if you look at alpha greater than beta greater than 1, then in this case what you'll get is something like that. So something like that kind of. And so here's again, it's again on the 0 to 1, but it turns out that in this case it's shifted a little bit to the left. And so kind of it gives a lot of possibilities for modeling. Also, kind of it is possible to have a shape like that. So kind of if alpha and beta smaller than 1, then you will get a you can achieve something like a shape like that. So for 0, 1, and here's alpha smaller than 1, beta smaller than 1. So by choosing different alpha and beta, it's kind of possible to fit many kind of, at least approximately fit many distribution on the interval from 0 to 1. Okay, so this is kind of role of it. So one thing kind of when we talk about is distributions, new distribution, we usually have something like a theorem about what's the expectation and the variance. So it turns out that in this case, kind of expectation is very simple, but variance is very difficult to remember. So probably kind of useful to remember the expectation, but the variance, well, kind of even in the case of uniform, there was a 1 divided by 12, which was kind of a little bit not kind of usual. So why 1 divided by 12? So in this case, so if x is distributed according to beta with parameter alpha and say beta, then beta small, then it turns out that x, expectation of x, well, and it's just a pure calculation, it's alpha divided by alpha plus beta. So maybe kind of, I'm not sure about this case, what I draw here. Yeah, this is probably wrong picture, right? So kind of maybe I should correct this picture. So, right? So because this formula shows expectation of x, it's equal to alpha divided alpha plus beta. So it's alpha greater than beta. Then expectation should be greater than 1/2, right? So kind of maybe this should be corrected. So it should be greater than 1/2. So the density should look like a kind of, it's shifted a little bit more to the right, kind of. So it should look like something like maybe that one, something like that. And so such that kind of you see that the most of the mass shifted to the right, kind of the middle of the interval. Okay, so this is expectation, and you see kind of this is kind of, well, it's alpha divided alpha plus beta, very easy to calculate. Right? And variance is a complicated formula which I kind of write, but I'm not expecting that anyone remembers it. It's kind of so kind of, but it's kind of exists. So it's alpha beta divided by alpha plus beta squared. So alpha plus beta plus 1. And so now in kind of a proof of this formulas is just by kind of just a regular method. So kind of you just go and integrate. So kind of, so for expectation, for example, of x, you would start with writing the integral. So 1 divided by, okay, so you would need 1 divided by this b beta alpha beta. And here's x multiplied by the density, and density here x to the power alpha minus 1. So here's 1 minus x beta minus 1 dx from 0 to 1. Right, and you see that this is kind of integral of the same type. Right? So this is integral also kind of it's x to the power of alpha 1 minus x divided by beta. So it's also can be formulated in terms of the gamma functions. Right? So, and after that there will be something like gamma of 1 thing divided by gamma another thing, and well, kind of there was some cancellation, and eventually we'll get to something like this formula. So just again, so for details you can see the lectures, but it's just a calculation of this integral, right? And we already have a formula for this integral, so we have this formula. So we find the integral of this type. So, and after that, some identities about the gamma functions will give you this answer. This gives you that this is equal to, after some calculation, alpha divided by alpha plus beta. And the same thing about calculation the second moment, and same kind of, if you calculate the second moment, then you will be able to calculate the variance. So this is how it's done. I skip it because it's kind of doesn't kind of add anything to understanding, except, well, this is a good calculus exercise. Okay, so now kind of so maybe kind of an example on this. So, okay, example. So in this example, so we have a x, which is um, say it's down time ratio of a machine. So it's kind of a ratio that the machine doesn't work because it's broken, kind of, right? So so since it's a ratio, it's a percentage of the time when the machine doesn't work. So since it's a potential that we know that x belongs to the interval from 0 to 1. So if it's 0, then it's always working. It's a very good machine. If it's 1, then it doesn't work. So it's very bad machine, kind of, right? So it's something in between, and we assume that it's distributed as a beta with the parameters, which is here 3 and 18. And then we ask several questions. So the first question is that, well, kind of very simple question. So what is the expected? What is the expected downtime ratio? Time ratio. And so this is easy, kind of expectation of x is equal to parameter, so 3 divided by 3 plus 18. Right? So that's it. So, and this is equal to 1/7. This is equal to approximately 14.28%. Right? So this is just simply from the formula. Right? So another thing is, okay, so what's the probability that a randomly selected machine is under repair less than 5% of the time? So second, a random machine so probability that a random machine under repair less than 5% of the time. So kind of, right? So if we choose a random machine, kind of, then this machine is pretty good, kind of, it's less than 5% of the time. Right, so it's much better than the average machine, because the average machine under repair is around 14% of the time. So what's the probability that this randomly selected machine is good? Right, so, and this is kind of clear. It says that the probability that this x, the downtime ratio for this machine, is smaller than equal than 0.05. You can see here that there is a small confusion. So kind of, so 5%, it's some kind of a probability, but so kind of we are looking at kind of this x is smaller than 0.05%. Well, kind of, and this is kind of something, this is clearly probability that this random variable smaller than 0.05. Well, we can write down the integral, but the integral, unfortunately, we will not be able to take it in the, it is possible to take it in the closed form, but it's kind of tough. So it's much easier to use a software. So in this case, we write it something like a p beta of 0. So this is clearly a cumulative distribution function. So we just write that this is p beta 0.05. And after that, we'll just need to know how we call the parameters. And it turns out that in the R, it's also called alpha. Alpha is equal to 3 and beta is equal to 18. So if you issue this command, then it gives you the probability. The probability is pretty small, and it's equal to 7.548, something like that. And so now again, so here's a 5%. It's the kind of the downtime ratio. It's kind of a percentage of the time that the machine is under repair. 7% is the probability, so that the randomly chosen machine is has a downtime ratio which is smaller than this 5%. Now, okay, so now after the third question that we can ask about this thing is a kind of a typical question. So it's kind of, it's a typical that you have a mix of in many questions it's typical that you have a phenomena which you model with one probability distribution by one random variable. So here's a downtime ratio. But it's also kind of that this is phenomena occurs in the sequence of the trials, several trials. Right? And so in this case, when if you have a sequence of the trials, it's natural to use the binomial distribution. So it's very often that you have two distributions, one of a kind of something like the kind of a beta or gamma, and another is a distribution which is related to the sequence of the trial. So something like a binomial or geometric distribution. There was an example of this in exam that we have a kind of, there was a Poisson and a geometric distribution mixed in one example. So here the question is, so if so the question is, what's the probability? What is the probability that in a sample of 25 machine at least three have downtime rates greater than 20%. Time ratios, maybe not ratio, rate here is used, ratio greater than 20%. And so we have a sample of the machines. So machine 1, machine 2, machine 3, kind of machine 25. So this is a shipment of this machine. And then kind of a look at this machine and look kind of this kind of, so this have one downtime ratio, so ratio 1, this is ratio 2, this is ratio 3, ratio 4, kind of, right? And so kind of we can kind of kill x1, x2, ratio 25. And so kind of, and so what's the probability that kind of at least 3 of them are very bad, kind of, they have a downtime ratio greater than 20%. So we model every of this ratio by using our random variable x, right? So x, and also we assume independence of machines. So kind of, right, so it's not that kind of, well, kind of it's one machine is bad and all other machines is bad. So kind of they are selected more or less independently from each other. And so now we model kind of every downtime ratio by this random variable x1, x2, x3, and so kind of, and after we model this kind of ratio, we see that this is something like a sequence of the 25 trials, and in 25 trials we ask the question, what's the kind of the probability that the more than 3 kind of are defective. And so kind of, so first thing to think, so first thing to figure out what's the probability one individual machine is defective. So probability that, so this would be x1, this is kind of would be x2, but all they are the same, right? So it's probability that x is greater than 20%. Yeah, so probability of a defective machine, to find a defective machine in one trial. Well, and kind of we already know how to do it. So we issue the common something like 1 minus p beta 0.2 now in, okay, so alpha is equal to 3, and so beta is equal to 18. Okay, so beta is equal to 18. And it turns out that this is equal to 0.20, so around 20%, 26 or 847, kind of not important, kind of, so right. So, and this is kind of, this is a probability that specific machine is defective, so we can think about as a P. Right? So the probability that we have a success meaning that the machine is defective in our 25 trials. So first, this is first step, and the second step, so the probability that we have a greater than 3, so what's the equation? Yeah, at least 3 have downtime ratio greater than 20%, greater than 3 defective machines. And so this is equal to the probability that the random variable y, which is kind of number of a defective machine in the shipment in the sample, it's greater than equal than 3. So where y is the number of defective machines in the sample. Right. So, and kind of, well, kind of, so from the previous calculation, we see that y is a binomial random variable. And so this is kind of a typical our problem. Y is a binomial random variable with parameter n is equal to 25, so 25 items in a sample, 25 trial, and p is equal to this thing that we calculated, 0.26 and so on. And so 61 approximately. And so this is again kind of can be calculated using R or using table. In this case, we just have that this is this probability that y is greater or equal than 3 is equal to 1 minus p, in this case binom, right? So binomial random variable. So here we should be careful. So probability that y is greater than equal than 3 is equal to the probability that 1 minus probability that y is smaller than equal than 2. So careful, because kind of, so here is a discrete random variable. So so p binom of 2 and size equal to 25, and probability probe equal to with 0.261. It turns out that if you calculate it, then this is equal to, so it's equal to 91%. It's pretty large, just because kind of, since the probability is 20%, 1/5. So then on average, a sample should have a 5 machine with this downtime ratio, right? So because it's p is about 1/5, right? So this p is about 1/5. Total sample size is 25, so 25 times 1/5 is equal to 5. So expectation of y is equal to NP is approximately kind of 5. So probability that it's greater than 3, well, it's certainly large, kind of, it's 90% in this case. Okay, so this is an example, kind of, then kind of where you model one random variable by using beta distribution, and after that use it kind of in another model, in a binomial model in this case. Okay, so, and kind of a typical example, then you can combine many kind of this thing. Okay. All right, so now Um, 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 so this is all about the beta distribution. So now what we have right now, what we studied, so maybe come and summarize. This is concludes that what we studied about the continuous random variable. So for continuous random variable, we studied uniform, right, distribution. And so and the density was f of x was equal to 1 divided by beta minus a, where x belongs to the interval from a to b. And it looks like kind of it just was a constant, right? So a, b, and the density was constant. And so this was 1 divided by b minus a. And so this was uniform distribution. So another was exponential. So maybe kind of another was normal, but okay, so let us start with exponential. Exponential distribution. This was a kind of, the picture was like that. And so this was 1 divided by beta, goes from 0 to infinity. And the density was f of x was 1 divided by beta e minus x divided by beta. And so the first uniform was a model for the something which is on the finite interval from a to b. Here is on infinite interval from 0 to infinity. So useful model for waiting times or kind of any kind of a time variables. And another kind of fundamental distribution was normal or Gaussian. Distribution. So it was a something like a kind of this is bell-shaped curve. And so it was here, it was a mu, and it was kind of extended for the whole real line. So kind of an approximately kind of 2 sigma. And so something like that. Kind of most of the mass was between 2 sigma, minus 2 sigma, and mu plus 2 sigma. So and the density was there. This case the density was looked very scary. So but it's kind of 1 divided by square root of 2 pi sigma squared e. Here's minus. Okay, so what was here? X minus mu square divided by 2 sigma square. So this was the density in this case. And so these are fundamental distributions. So everyone should know this. This is absolutely fundamental. And after that, we started to study a little bit kind of like a generalization of this thing. So there was a gamma, right? So which was a kind of a generalization of exponential. So the gamma distribution, we look at kind of a exponential is here, and we a little bit change it, kind of, we'll say, so let us multiply it also x alpha minus 1, e minus x beta, add additional parameter here, and kind of, well, it turns out that here we'll need beta to the power of alpha and gamma of alpha here. And also was a kind of an x is greater than 0. So the picture here changed a little bit, right? So it could be now kind of something like that one. And so beta again controlled what's the shape of, sorry, beta controlled what's the scale of this distribution, and alpha control what's exactly the shape of this distribution, right? So this was a gamma distribution, right? So generalization of exponential. Another was a thing that we studied today was a beta, and this was a generalization of the uniform on the interval from 0 to 1. So here's f of x was equal to 1 divided by some constant, and here's x alpha minus 1, 1 minus x beta minus 1. So for some values of the parameters, gamma distribution reduces to exponential for the parameter alpha is equal to 1, and beta distribution reduces to uniform distribution when alpha is equal to 1 and beta is equal to 1. And so the picture is here, so something like that one, kind of, right? So from 0 to 1. Right? Of x. Okay, and this is a kind of more, this is kind of generalization. So you kind of learn it because, well, this is one possible generalization. So it turns out that there are many, many other kind of distribution. In fact, it's very easy to invent a distribution, take any function which is a positive, right, on some interval, and normalize it by the integral. So divide this function by a constant which is equal to the integral of this function on the kind of region where you kind of consider it. So kind of you can invent a huge number of distributions, right? And many of them are used in the analysis, in modeling analysis, and the popularity changes over time. So recently there was a popular distribution which is logistic distribution. So I will not define it, but kind of just mention the name. So logistic distribution, very popular in the kind of in econometrics, and recently it was popular in machine learning, in many other distributions. So Weibull distribution. We will learn a little bit about a little bit later about T distribution. So Weibull distribution, Cauchy distribution, which is famous because it doesn't have an expectation, right? So so you cannot find out what's the expectation. It's symmetric, it looks like Cauchy distribution, for example. All of them are Weibull I don't know, but logistic distribution, it looks very much like the normal distribution, but it's a little bit different, and useful for analysis. Right? Cauchy also looks similar to this thing, but they have very heavy tails, so that it's symmetric, but it doesn't have an expectation. Right? So there are many of these distributions, and if you encounter one of them, then most of them are modeled in R, so you can just go to R, look at the help, and you can find the helpful logistic, Weibull, and Cauchy distribution in there. And so again, it's a huge number of these distributions. We just studied 3 fundamental distribution and 2 possible generalization, which popular, and were selected in this book. Okay. So now maybe let's make a break right now. It's a little bit early, but let's make a break because we finished this chapter essentially. So if you have a question, so you can ask a question now about this. After the break, we will probably start next chapter talking about multivariate distribution. All right. So 5-minute break.
Professor?
Yep.
Is there any way that you can post the chapter 5 lecture notes?
Yeah, yeah. So usually I look at this chapter, and so do some. I actually, I update these chapters, right. So if you'll notice, when chapter 4 is already not the same as it was when I posted it first, right. So, but right now I just started to looked at chapter 5, and probably I'll post it today, right. So chapter 5.
Thank you.
Yeah. Also, I think that I owe you the video from the previous lecture. So I'll also post the lecture. Okay, so. Okay, so let's restart. So what we are going to start is multivariate distributions. Multivariate distributions. Multivariate random variables. And then, so the idea is that we started. So the motivated random variables is that this is kind of simplest case of the experiment. So usually we have an experiment. So usually our picture, experiment results in outcome, gives outcome omega. And then we looked at the simplified version of experiment, which kind of you can say that the experiment gives just one number. This was a random variable. And so so we can say that x of omega is a random variable. And so it's kind of, we can think about this as a feature of the experiment. We look at one feature of the experiment. Right, so, and this was just a kind of a real number. So now we can look at the situation when this experiment results in several random variables. So we can look at the x1 of omega, so x2 of omega, and so on, xn of omega. So n random variables. So one, maybe two, maybe kind of more random variables. So we look at several features of the experiment, which is next step kind of in the study of the randomness. And well, there are many examples of this. So kind of some of them are listed in the kind of lecture notes in the books. So examples. So so we can say omega is a random household. So we have a population of the households, say US households, and we choose one of them. So in this case, we can have x1. Well, it's a function of this omega, right? So x1 is an income, a household income, x2 is number of children in the household. So this is one example. Right, so it kind of, so it kind of gives them more information, so we can study just household income or just the number of the children in the household. But typically there is some relationship between the kind of household income and the number of children. They kind of can be, you can say that if there are more children, then the household income is larger, something like that. You can start to study whether there is some relationship between two random variables. And then there are plenty examples of this. So second kind of, so say a school student in a school, and kind of you can look at the kind of you can measure the IQ of this student. So and kind of you can also look at the history of the student and see what was the birth, the weight of this kid at the birth. So the birth, the weight at the birth, birth. And then again, the idea would be kind of to see what's is there some relationship. So maybe kind of it's more kind of you can gain more insight in the situation if you look at the both of these random variables. We're just looking at one of them. And another kind of an example kind of could be something like a passenger a Titanic and X1 kind of a indicator of a gender, indicator of passengers gender. So whether it's a female or a male. And the next two is kind of survival indicator. So you can also kind of see kind of whether these things are related or kind of, so kind of it clearly gives more insight in the situation than just looking at one of these variables. So kind of, and this is in this example we look just on the two random variables, but in principle it could be more kind of, so right, so kind of in principle, for example, it even maybe that you don't know how many kind of the random variables you want to look at kind of. So for example, you can look at the kind of a counter of particles kind of as before, kind of counter of particles and say that kind of xi is the time of arrival of ith particle. So this is a kind of a more difficult situation. So maybe we'll not cover it here because it's not clear how many. So the number of particles is also random, right? So in this case, right? So, but kind of this is more kind of gives you more information about the situation than counting how many of the particles, for example. Okay, so and okay. Now another example kind of can be, so in principle it could be that the kind of the number of the variables is very, very large. So if you look at this, for example, in an image, so this is kind of a random image. A random image. So kind of maybe kind of you can say that's kind of so 25 by 25 RGB image. And so what it means kind of, so it means kind of you have a kind of what it this means. So you have a image which is kind of the size of this image is 25 by 25, meaning that kind of at every point, so this is kind of like a matrix here, at every point you have a intensity. So in every point you have a intensity, so xi is the intensity of a pixel, which is in this specific position, right? So there are kind of 25 pixels in every column, 25 pixels in every row. So you have a kind of, you can represent the image as a matrix of the intensities of the pixels. And since it's RGB, kind of it turns out that you kind of also have a kind of free intensities for every color, for red, for green, and for blue. Kind of, so it's a kind of multiple. So in the red channel yi, so intensity in the blue channel, so green channel, and zi, intensity in the of the image in the blue channel. Where with I Okay, so this I, it's the number of the pixels in the image, right? So I can be it ranges from 1 to 25 times 25. So so this collection, so how many random variables you have here? You have a 60, 25, so 25 squared multiplied by 3 random variables. Which describe the image, right? So this is maybe extreme example. So you can have a lot of random variables which describe some random phenomena. And even if you look at the one individual, then you can look at if you look at the record of this individual in the hospital, you can have a lot of characteristics about this, right? So now so this shows you that it's important to have some ways to analyze this distribution when we have many random variables, many features which describes one random situation, one random outcome of the experiment. Right, and so right now what we are going to do is to look at the basics of this description on the how on the joint distribution of the random variables. So in comparison with the univariate distribution, it's much more complicated, right? And we will see it later in the fact that there are not many models, right? So we had many univariate distributions which can be used to model univariate random variables. But it turns out that there are not many models of the multivariate, not many standard models of multivariate random variables. So it's shows that this is more complex situation. Okay, so, but let us start with something like a basics. Okay, so the basic is a joint distributions. Right, and so we start with a start with very simple things. So first of all, we assume that we have just two random variables. So in principle, it can be 6025 multiplied by 3, but the basic ideas will be the same as for the two random variables. So assume two random variables. And for now, assume also that these random variables are discrete, right? Because it's simpler, when we're talking about continuous. We don't need any densities or something like that. We just need probability of the outcomes. So assume random variables are discrete. So, and after that, we can generalize to continuous random variables. So in this case, so a definition is a basic definition is a PMF. So joint PMF, joint probability mass function. So PMF is defined very naturally, So we define it's P. So here we'll call this random variable x and y. Okay? So the Px of y, so of x and y, it will be just equal to the probability that random variable x takes value x small and random variable y takes value y small. Okay, so this is a joint probability mass function. So now another definition is marginal PMF of random variables x and y, kind of the usual PMF of x and y. So px of x is equal to the probability that x takes value x, and py of y is probability that y takes value y. So this is kind of our usual. There is nothing new here, so except the word marginal. So we use the word marginal just because that this is a situation when we have two random variables, and well, kind of, well, if you want to say PMF over two random variables, when we say joint PMF, if we want to say PMF of one random variable, we say kind of marginal PMF. And so, and the reason for this is that sometimes we are just given the joint PMF and asked to figure out what's the probability mass function for one random variable. Right? So kind of, so in this case, so this is kind of the first theorem or kind of result, but it's kind of obvious. So Px of x small is equal to, okay, so if you want to figure out what's the probability that x is equal to x, and we given all the probabilities of this type, then we sum of all possible y values. And so so here we'll have a sum over all possible y's. And so and here is pxy of xy. So here's an example of this thing. So example. Right? And so let's look at x is, so let's look at the, let's look at the experiment. So first of all, let us say what's the experiment here. So 2 die of toast. So x is the number on the first die. And say, let us look at the s is the sum of the values on both dice. So okay, so what's the experiment? The experiment can have a so the experiment, well, can clearly have a 36 outcomes. Right? So now, what about the joint PMF? So let us look at the joint PMF for x and y. So we can visualize it as a table. So the table says, so what's the values for x? So not a y here, so maybe kind of here, sorry. No, it's a good, so maybe y, kind of, not s, but y. Sorry, so I use s as a sum, but let us use y here. So consistent with what did before. So we can have a values for x and values for y. And for x, what's the possible values for x? Possible values, maybe kind of even kind of, let me change it here, say, let us say x is here, y is here. So now for x, the possible values for x is the number on the first die, so it can be 1, 2, 3, 4, 5, and 6. And for y, it's the sum of the values on the two dice. So it could be 1, so it cannot be 1, right? So it cannot be 1 because the sum is never 1. So it should start with 2. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so these are possible values on the possible values for the sum. And so, and after that we are saying, okay, so what's the probability that x takes value 1 and y takes value 2? And so, okay, so this happens if the second die have the value 1 as well. So now this is the only possible outcome here. And so this is the outcome. This, if we have a random variable equal x to 1 and y equal to 2, this is only one possible outcome, which is 1 and 1. And so the probability that we have x equal to 1 and y equal to 2, it's equal to 1 divided by 36. 36 is the total number of the outcomes. Right? Now, kind of the probability that x takes value 1 and y takes value 3, well, it happens when we have an outcome 1 and 2. Right? So this is the value of x, and the sum should be equal to 3. So again, so here's 136, and we can continue 136, 136, 136. 7 is also possible, so it's 1, 6, right? So it's 136. And for 8, it's not possible. So the probability of this is equal to 0. So and after that, 0, 0, 0, 0. And now saying what's the probability that x is equal to 2 and y is equal to 2 as well. And so the probability of this is 0. It's never possible. If you have already 2 on the first die, then on the next, on the second die, you will have outcome equal to 1. So it's, the sum will be definitely greater than 2. So it's greater than or equal than 3. So here's 0. And after that again, so here's 136, right? So because it's the only possible outcome here is this is 2 and 1. Right? So this, and the probability of this single outcome is 136. And after that we continue 136, 136, 136, 136, 136, 136. Right? But so 9 is not possible. 8 is possible because it's 2 and 6. But 9 is not possible. So here 0, 0, 0, 0, and kind of you can see that how you can kind of construct this table, right? So here will be 3, x is equal to 3 and y equal to 2, not possible. X is equal to 3 and y is equal to 3, not possible. But the x equal to 3 and y is equal to 4, it's possible. It's equal to 1 divided by 36, and well, kind of again, so there will be 136, 31, 36 here, 136 here, and after that 0, 0, 0. So now how it ends this table. So after that you continue this table, right? So kind of this is for free. You can continue this table how it ends. And so, okay, so ends, okay, for 6. Right? For 6, it's here we'll have a 6 and 6 is possible. Right? So here we'll have a 136. 11 is possible, 136. Right? 10 is possible, 136. Right? 9 is 6 plus 3, also possible, 136. 8 is possible, 136. So which one not possible? It's 6 and 0, right? So kind of 6 would not be possible. So have a 136 here, and 6 is not possible. It's 0 here, right, in this column. Right? So this is kind of a table which is visualize our PMF. So you can think about this as a table. Right? So now, kind of, for example, we'll have a px of y of say 3 and say 6. Okay? So this is the entry here, right? So which is equal to 136. And so this is a PMF. Okay? So now, kind of, what about so I say p of x, y of say 3 and 2 is equal to 0 because it's kind of this is entry here. And so now what about the marginal? So this is a joint PMF, and it's summarized in this table. What about the marginal? PMF. And so now to calculate the marginal PMF, and so if we want to use our formula here, the formula which we had in this theorem, so it just says that if you want PMF for random variable x, then we'll need to say overall possible for this fixed x for all possible values of y. And so now, so for example, for x is equal to 1, and so let us look right here as the px of x. And so x is equal to 1, so this is x small is equal to 1, then we'll need to sum over the whole row for y equal to 2, y equal to 3, y equal to 4, y equal to 5, right? So y equal to 6, y equal to 7, and so on. So the sum is kind of 136 continued 6 times, so the sum will be 1, 6. And so kind of you can see that in every row it will be the same thing. So 136 added up 6 times, so 1 divided by 6. So 1 divided by 6. So in this case, the marginal distribution for x is equal to 1, 6. And it's obvious before kind of this calculation, because this is a random variable, just number on the first die. And we know that this is equiprobable. Right? So it's equal to 1 divided by 6. Right? So this is a marginal distribution for x. And what about marginal distribution for y? And so it turns out that in this case, so p of y of y, we'll just need to do the same operation. We'll need to sum, but now over the columns. Right? So there will be 136. After that will be 2 divided by 36 because we are summing these two elements here. After that we sum, here we have a 336 and so on, right? So kind of until we reach to 7, then we'll have a 6 divided by 36. And after that, the kind of a probability starts to decline. So we'll have a 5 divided by 36. This is 4 divided by 36. Right? Because this is kind of, this is kind of, so here we sum this column here. And so there are 4 elements here, right? So for 3, for 4, for 5, and for 6, and the sum of them will get 4 divided by 36, and so on until we get eventually get here 1 divided by 36. And so now this is a marginal distribution for y. Right? So now we calculate it using, it's possible to calculate it kind of without using this thing, but without using the joint distribution. And so we at some point we calculated this PMF without using the joint distribution of x and y. But this is example how it can be calculated using the joint distribution of x and y. All right. So that hopefully this gives you the idea of the relationship of a joint PMF and marginal PMF. Okay, so and also kind of explain the name marginal. So we kind of have a big table. Okay, so we have this big table here, and we calculate the sums of the rows, sum of the columns, and write it in the margins of this distribution. Right. Okay, so maybe kind of a couple of more examples. So we'll introduce another example which we'll use kind of as a standard example for our concepts. So so here's another example, and it says free universities or researchers of free universities apply for 2 grants. Apply for 2 grants. And so, and we have so kind of, so for concreteness, let us say universities at New York, can think about Binghamton, so at say Florida and California. So California California and Florida. Right. So for shortness, we will write, so this is for New York N, for California C, and for Florida F. Right. Right. So now the random variable will be X. So this will be amount, so the number of grants. So number of grants awarded to New York. Okay, so and Y, number of grants awarded to California. Okay, so it's not so important but it's just number of grants awarded to one university and one number of grants awarded to another university. And with for specificity, we choose New York and California universities. And so now all right. So assume that this is a purely random process. So everything there is no advantage of one university over the other, and the grants are awarded purely random fashion. So first grant some random process, and the choice of New York, California, Florida is equally probable. Okay, so now so first question is what's the joint PMF of X and Y? And then again, so we can write a formula for this thing, but it's in this case, so it's a number of outcomes small, it's easier to represent it as using a table, right, as before. So we have here as say X, and so here's a number of, so this is the values for random variable X, and this is values for random variable Y. So maybe I should also write it in the previous table also here. Should be maybe not X large and Y large, but X small and Y small, right? So it's a value, possible values for random variables X and Y. And so now, okay, so and so what's the possible values for X? Right? So there are only 2 grants possible, right? So we have a possibilities that no grants are awarded to New York University. 1 grant is awarded to New York University, or 2 grants awarded to the New York University. So we'll have here as 0, 1, and 2. Right? And for Y, it's totally symmetric, so 0, 1, and 2. Right? So we need to fill out this table and see what's the probability that X and Y is equal to some specific values, right? So in this case, this is again, so nothing difficult. It's just listing the all possible outcomes, and they are all equally probable. So all possible outcomes, we can list it this way. So NN, which means that both grants are awarded to New York, both to New York. Right, and after that, okay, so what other possibilities? And C, so which means that first grant is awarded to New York, the other grant is awarded to California. And F, right, and so on, right? So it's easy to list them here. So all nine possibilities. 3 possibilities for the first grant to be awarded to some universities, so 3 possible universities, and 3 possibilities for another grant to be awarded to university. So 3 times 3, 9. So it's small, and we can list them. So CN, right? So California got the first grant, New York got the second grant. Right? And after that will be C, California got both grants, CF, FN, FC, and FF. And so this is a possible outcomes of this experiment. And after that, we just count. So X is equal to 0 and Y is equal to 0. And so this corresponds to this situation, right? So C and C. So because it's means that X is equal to 0 means that New York got 0 grants. Y is equal to 0 means that the not that so this is wrong kind of, right? So okay, so so it means that this California got 0 grants, so it means that Florida got above grants. So it should be this one. Right? Okay, so here's one possibility. Just one possibility. Okay, so now after that we analyze the other similar. So kind of, so what about X is equal to 0 and Y is equal to 1? It means that the California got 1 grant and New York got 0 grants. So this can happen only when, okay, so this situation, California and Florida, or in this situation, Florida or California. Also kind of here should be have a probability. So this should be not 1, but 1 divided by the total number, right? So 1 divided by 9. Right? So the total number of possibilities is 9. Right? And they're all equally probable. That's why kind of 1 divided by 9 possible. Right? So here will be 2 divided by 9. So this is kind of this California, Florida, Florida, California. And so X is equal to 0. Y is equal to 2 means that the California got both grants. So this case. Right? So this means that this is here will have 1, 9. One possibility. Now this is all everything symmetric, right? So here should be the same thing, but kind of, right? So kind of, there is no difference here between California. So here there should be 2, 9, 1, 9. Okay, so now what's other possibilities? So 2 and 1 not, so kind of what's 1 and 1? What 1 and 1 means 1 grant to New York, 1 grant to California. There are 2 possible cases. So this one, right? So this one and this one. New York, California, or California, New York. So again, so here the probability is 2/9. Now, and all other kind of entries should be 0 because 2 grants to New York and 1 grant to California clearly not possible. There are only 2 awards. Right? So here 0, 0, and 0. And so this is a kind of a joint PMF of X and Y. And so from that we immediately can calculate what's the marginal PMFs. And so so here we'll have a px of x. Okay, so for every possible values of x, we can figure out what's the probability that the random variable x, number of the grants awarded to New York, what's the probability of this? So probability for 0 is equal to 1, 9 plus 2, 9. So it's equal to 1, 9 plus 2, 9 plus 1, 9. And so we summing those things together. So it's equal to 4, 9. Right? And so on here. So here's again 4, 9. And here is equal to 1, 9. So this is a marginal PMF for x, for random variable x. And by symmetry, it's exactly the same for y. So we write here py of y. Right? It will be 4, 9, 4, 9, and 1, 9. Also it's by symmetry, but also you can sum the columns here. And sum of the columns gives these numbers. Okay, so this is a joint and marginal PMF. And so now, how about the calculating the probabilities using these tables? And so this is kind of why we'll need this thing. So calculating probabilities using joint joint PMF. So, and the formula kind of, we'll just need to sum overall individual outcomes. Right? So sum the PMF, joint PMF, of all possible combination of values which belongs to our event. So probability that X, so formally probability that X and Y, right, belongs to some event A, right, it's equal to the sum of X and Y belonging to this A of P X, Y of X small and Y small. So, but it's maybe easy to see from the example. Say, let us look at this table and calculate the probability that X is greater than equal than Y. That, well, kind of, that New York will get at least as many grants as California. And so now how we can do it? So we can write, so we can look at the kind of, it should be equal to the probability and look at all the cases when this event is true, right? So when X is greater than Y. So what's this event? It's this one, right? So the cases when X is greater than equal than 1. So okay, so this is okay. So 0 is greater than 0, 1. Okay, so it's this thing. So 1 is greater than 0 and 1 is greater than equal than 1. And 2 is kind of 2 is greater than equal than 0, greater than equal 1, and greater than equal 2. So this is our event of interest. Okay, so this is exactly the values of X and Y such that this condition is satisfied. Condition that X is greater than Y is satisfied. Okay, so and our rule says we'll need to sum over all possible values of PMF inside this event. So we'll need to sum over all possible things all possible values of X small and Y small which satisfy this event. So it's equal to P of 0, 0 plus P of 1, 0 plus P of 1, 1 plus P of 2, 0 plus P of 2, 1 plus P of 2, 2, right? I wrote it all things because you can see here, well, I included only those things that X small is larger than Y, larger or equal than Y, kind of, right? So the formal, this is a formal thing. But if you look at the table, you can clearly see that kind of from the table, it's clearly seen that it's equal to 1/9 plus 2/9 plus 2/9 plus 1/9. So if you sum it all together, we'll get a 6/9. So it's equal to 2/3. Okay? So the probability that the New York University gets at least as many grants as the California University is equal to 2/3. So this is kind of a basic idea how you calculate the probabilities using the joint PMF. Okay, so and this is the same as we do univariate case, right? So except that kind of here where the event can be more complicated. And so then in the univariate case, it was kind of just kind of something simple. Here, this is a sort of like a triangle of the outcomes includes and kind of, so the shapes can be more interesting. Shapes of the events can be more interesting. All right, so okay, so maybe kind of it's time to stop here. And we started this topic, and this is the fundamental concept, joint probability mass function and marginal probability mass function, and how to calculate the probability using the joint probability mass function. So next time we will go to talk about conditional PMF and also about conditional expectation. Right? But let's stop here. So if you have a question, so any question about the lecture or about something like organization questions, so you're welcome to ask questions. Otherwise, so well, yeah. Have a nice day and see you on Friday.
Thank you.
Thank you, Professor.
Thank you, Professor.
Yeah, I see some problem. Okay. Yeah, thank you. Yeah.
Hi, Professor.
Yeah.
I had a question. Could you go back to the notes where you write the example downtime ratio of a machine, like the beta distribution?
It's for beta, right?
Yeah, like last chapter.
So it's a different. Yeah, this is here.
And the example you write the downtime ratio of a machine.
Yeah. Yeah, here. Yeah.
Yeah, right here. So I was wondering, like, how do you like solve the calculate the CDF for beta distribution without using the any software like R, but just using by hand? Like for example, this one like P x less than equal to 0.05, and you use, I know it's like how you do this.
Well, for these values of the parameters, I don't know how to do it. If it would be something like a small values of the parameters, right? So if it would be something like 1 or 2, then in principle, this is a doable integral, right? So kind of in principle, you would have something like a from 0 to say 0, 0, 5, and after it goes something like a kind of, so x alpha minus 1, 1 minus x beta minus 1. So if this alpha and beta are small, then you can do this integral, right? So it's a polynomial, so you can calculate it. And so it may be divided here by beta of beta alpha. And so in principle, you can calculate this integral if alpha and beta is small, because in this case, well, so if beta is equal to 18, well, still you maybe kind of do a change of variables, kind of, right? So, but if both of them are large, and if beta is large and alpha is small, then you can change variable and say y is equal to 1 over x, and you will get something like y to the large power, which is not so bad. And so you would get something y to the power of 18 minus 1, and here you will get 1 minus y to the power of 3 minus 1, right? And this is not bad. Even in this case, it could be doable, right? So this is what can be y. 1 minus 2y plus y squared. Here would be y to the power of 17 dy, right? So maybe I'm not sure what sign is changing. No, probably sign is not sure about the change of the sign in this integral. And so because you do the change of variable here. And so, but well, this is a kind of doable integral, right? So, right? So in principle, you can do it without going to software, but okay. So not, yeah, doable, but well, if you need it, if you must do it, right? So,
got it. Yeah, but what's the 1 over b of beta and alpha represents, like in the front parameter?
So this is a part of a density, right? So this is a part of a density, and this is, I think that this thing altogether should be equal to gamma of alpha plus beta divided by gamma of alpha gamma of beta. So in this case, so kind of it should be equal to so what we'll have 18 and 3. So gamma of 21, right, divided by gamma of 3 gamma of 18. So it's equal to 20 factorial divided by 2 factorial divided by 17 factorial. Right, so okay, so it's 20 times 19 times 18, right, divided by 2. So this constant is equal to this thing.
Got it. I see.
So it's still kind of doable, right? So
right. I see. All right, that makes sense. Thank you so much. Have a nice day.
Yeah, you too.
Bye.